Chapter 17, question 5 says methyl orange is an indicator used for detecting the pH of acidic solutions. This is a really good indicator that we use whenever our titrant is a strong acid because we expect that equivalence point to be in an acidic, a much more acidic area. So it says the red protonated form of the indicator, which is the HIN. So IN just represents for indicator, it's just a weak acid. It dissociates into a yellow deprotonated form. So the second the solution becomes basic, it goes from a red color to a yellow color. And then the pKa for methyl orange is 3.4. Then it says, identify the color of solution containing methyl orange indicator at pH of 2. So if the pKa, so the pKa represents where there's equal amounts of HIN and IN. So that's just whenever there is a 1-to-1 ratio of HIN to IN minus. So if there's an equal amount, then technically the pKa will have a color of around orange. It'll be between red and yellow. So anything that's more acidic, meaning that there's more HIN in solution, that means that the predominant color is going to be red. Whenever there's more IN minus, or the conjugate base, the solution is going to be predominantly yellow. So when we're asking these questions, identify the color of solution whenever the pH is 2, what is the predominant species? So at pHs of 2, that's a much more acidic number than the pKa, so the predominant species is going to be HIN. So the color is going to be red. Okay. B says identify the color of solution containing methyl orange at the pKa. So if the pKa is 3.4, there's equal amounts of HIN and IN minus in solution, so it's going to be between red and yellow. So the only color that's between red and yellow is orange. And that's when HIN is equal to IN minus. And then lastly, identify the color of solution containing methyl red at a pH, methyl range, indicator of a pH of 6. What is the predominant species at pH of 6? So that's a much higher number than our pKa. So our predominant species is going to be the conjugate base. And so the color is going to be yellow. And I know that's not a very easy thing to see, so I'm just going to say yellow. Chapter 17, question 6 says, consider the following table of indicators and their properties. Which indicator in the table is best suited for confirming that a water sample is neither acidic or basic? So if we're looking for neither acidic or basic, then the pH is going to be 7. So if we look at the indicators from the table below, which one of these indicators can change color in the pH range of 7? It's going to be bromothiamyl blue. Question B says which indicator in the table is best suited for a weak base strong acid titration where the equivalence point will be at a pH of 5.9. So if I was to draw this quick titration curve, it'll look something like this. We have a weak base and it goes into a strong acid. And so that equivalence point is going to be at a pH of around 5.9. So when we're picking an indicator, that color change needs to be after the endpoint, or at least right after that endpoint. So while if I reverse this and had a strong base as my titrant, it would need to be up here. We have a weak acid as our titrant, so that means that the overall pH is going to be much smaller. So when we pick an indicator, we need to find an indicator that is right after 5.9, but on the lower end. So if we look at our options, the two acidic numbers we have are methyl orange and bromocresol green. But which number is right after 5.9? It's going to be bromocresol green because it starts the change at 5.4 to 3.8. So that means that the color change is going to be right after that equivalence point, and that's going to be where the end point is. If we picked methyl orange, it honestly would not be that bad of a decision, but the question is, what is the best indicator? The best indicator is going to have the color change right after the equivalence point. Methyl orange is just a little bit further away than our liking. So for this one, it's going to be bromocresol green. Question C says, which indicator in the table is best suited for a weak-base strong acid titration, where the equivalence point will be at a pH of 4.5. So we need to figure out which indicator is right after that pH change, or that equivalence point. So if our equivalence point is 4.5, and we know the strong acid is the titrant, so it's going to look something like this, and that equivalence is around 4.5. Then we need to come up with a color change that's right after that equivalence point on the lower end. So looking at our options, our two acidic are methyl orange and bromocresol green. The one that is right after 4.5 is going to be methyl orange. So that's going to be the answer to C. Okay. And then part D says, which indicator in the table is best suited for a weak acid strong base titration, where the equivalence point is at a pH of 8. So now our titrant is a strong base. And if our equivalence point is around 8, then we need to pick a color change that's going to be right after that 8. That's where the indicator is going to change. So looking here, there's really only one basic indicator, and that's phenolphthalein. So that's our only option here. So it's going to turn from a colorless to a pink whenever we get right past that 8. Chapter 17, question 7 says the indicator bromophenol blue is yellow between pH of 3 and yellow below pH of 3 and blue above a pH of 4.6. Then it says we've added a drop of bromophenol blue to a solution of 1.4 times 10 to the minus 3 molar HClO4. What color will the solution become? So essentially we need to know what the pH is. If we know what the pH is, we can kind of decipher what the color is. Another thing to know that HClO4 is a strong acid. I also have tested y'all on HClO before. That is not a strong acid, that is a weak acid. So make sure you know the difference. HClO4 is a strong acid, so it completely dissociates in water, and we can calculate the pH just using the concentration. All right. So the pH is just going to be equal to the negative log of that concentration, so 1.4 times 10 to the minus 3. So the pH is 2.85. So now let's look at our range. It is a yellow color at pHs below 3. And it is a blue color at pHs greater than 4.6. So our pH is lower than 3, so the overall color of the solution will be yellow. Sorry, I know that you can't really see that, but I like to keep the colors. So yellow is the answer. Chapter 17, question 8 says, in a saturated aqueous solution of MgF2, the magnesium ion concentration is 2.64 times 10 to the minus 4, and the fluoride ion concentration is 5.29 times 10 to the minus 4. Calculate the solubility product for MgF2. So we need to actually set up the equation before we can plug in numbers. So I have MgF2. And if they mention the solubility product, I know that that compound is going to be a solid. So when I break it up, it becomes Mg2 plus aqueous. And then I have 2 fluorides, aqueous. So if I'm going to set up my KSB expression, it's just going to be the concentration of Mg2 plus times the concentration of F minus squared. And they were nice enough to actually give us those values at equilibrium, so we can just plug in those values and calculate the KSP. So KSP is equal to 2.64 times 10 to the minus 4, that's magnesium, times 5.29 times 10 to the minus 4, that's fluoride, and don't forget to square it. So the KSP is 7.39 times 10 to the minus 11, and there's no unit, so it's just that value.